For this next Q&A, where I'm going to be answering questions from the back of the book, we're going to focus on the Bohr model of the atom. So let's take a quick look at Bohr's model of the hydrogen atom, and this applies to other atoms as well. Okay. So for Bohr's model, of the hydrogen atom. So a little background, first of all, is the hydrogen atom is the simplest atom out there. It has one proton and one electron, or 99.99% of the atoms. The other 0.01% have one proton and one neutron, which could affect how the atom behaves. So this model is for the H1 atom with one proton and one electron. All right, so for his model, the idea was that the electron orbits the nucleus. So it actually circles around the nucleus. Another part about this model is that the electron orbits the nucleus only at discrete distances. So imagine, if you will, what we're talking about for discrete distances is like talking about how far you are away from a wall. Now, you could shimmy up to the wall and take tiny little steps and be as close or far away from the wall as possible. But imagine if you could only take steps, not a half step, not two steps, but one step at a time. Then you would only be discrete distances from the wall. So with this model, you're at discrete distances. So when you have your proton in the middle of the atom and your electron is orbiting the atom, it can be at either the first level, it could be at the second level, it could be at the third level, and so forth, but it could not be at 1.2 or 1.5. So the electron would actually have to jump from one level to the other and change its distance, instantaneously. Okay. When you have the electron orbiting at discrete distances, there's an energy associated with the electron. So the energy associated with the electron is negative RhC over n squared, where R is Rydberg's constant. Now, I always have trouble remembering this one, but it's like 1.097 times 10 to the 8th, meters, seconds, or something like that. We'll look it up in just a moment. H is the Planck's constant. And Planck's constant is 6.626 times 10 to the minus 34 joule seconds. C is the speed of light. And the speed of light is 2.998 times 10 to the 8th meters per second. And n is the orbit. So for the first orbit, it's 1 squared. For the second orbit, it's 2 squared, and so forth and so on. Now, it looks like the units here have to be per meter for things to work out. Now, let's double check and make sure that that is the constant for Rydberg's constant. So I'm opening up to chapter 6. And I'm looking on page 2. I can't find it. Page 284. And Rydberg's constant is 1.0974 times 10 to the 7th. 10 to the 7th per meter. Okay, so I'm going to cross that out so you can see that more closely. 1.0974 times 10 to the 7th. And the book says meter to the -1, which is the same as saying per meter. So this is the energy of an electron. Now, the reason that there's a negative sign here is because the electron is actually attracted to the nucleus. So when these charges are attracted to one another, we give it a minus sign. And when they're repelled from one another, you give it a positive sign. Okay, so there's a Bohr's model of the hydrogen atom. Furthermore, if we take a look at the hydrogen atom, you can actually get the electron to change levels. So here's your proton. Here's your first level. Here's your second level. So let's say you have an electron at the first level. You could actually absorb a photon of energy. And when you absorb a photon of energy, that electron could become excited. So this is called the ground state, where the electron is in the most stable orbit. Here, the electron has traveled to the second orbit because it's absorbed this energy from the photon. And a particular photon will do this, not just any photon. It has to be the right energy for the electron to go up in energy. Okay, so this is called an excited state. And this happens when you absorb energy. Now, turns out that the electron can relax. And we call this an emission. So the electron goes back down into the first state, and energy is emitted, and that energy emitted is going to be a photon. And that photon will be the same energy as the one absorbed. Okay, so here we have the ground state again. Now, this does not have to happen between the first and the second level. It could happen between the first and the third level. And the amount of energy absorbed would be different because it takes a greater amount of energy for the electron to be forced out farther away from the nucleus to the third orbit. And likewise, if the electron were in the third orbit and it relaxed to the first orbit, it would emit more energy because it would become even more stable than from the second orbit. Likewise, you can have electrons go between 2 and 3, or 3 and 2, and so forth and so on. You can have any number of jumps possible. So there's a number of different energies that could be absorbed that could cause a change in the position of the electron. So the important thing here is that to get an electron to go to a higher orbit, farther from the nucleus, you have to absorb energy. And when the electron comes back down from a higher or excited state to a less excited state or the ground state, it's going to emit energy. Now, what happens when these things relax and they emit energy? When they emit energy, we're going to see a line emission spectrum. And the lines correspond to the energy of the photons. So different photons have different energies. You remember the formula, E equals hc over lambda. So for different energies, you have different wavelengths of lines. Now over here, what you would have is a line absorption spectrum. So if you shined light at this electron, certain wavelengths of energy would be absorbed, and those wavelengths would not make it through. So you would see these little black lines in your absorption spectrum. So here, these are colored lines. And here you would have black lines corresponding to wavelengths absorbed. Okay. And let's see if our book has a good picture of this for us to look at. I think it does. So right here, this is a line emission spectrum where you basically do something along the lines of this. We're going to zoom in on this a little bit. Do an autofocus. Okay, so here you have a bunch of hydrogen atoms that are excited with electricity. So these electrons are at the n equal 1, 2, 3, 4, 5, 6, 7. They're at all sorts of different states. And this light is passed through a couple of slits here to orientate the light all in the same direction, and then through a prism. And here's your line emission spectrum. Now, these lines that we see, of course, are the visible range. So each one of these lines corresponds to an electron dropping from one level to another level. Okay, let's see if we have an absorption spectrum. Our book does not have an absorption spectrum, so I'm going to use this to describe an absorption spectrum. So imagine, if you will, that this is not hooked up to electricity, but it's just a cylinder of hydrogen gas. And behind here, we put a lamp of visible light with all of the wavelengths of visible light. So when you shine the light through here, through the hydrogen gas, what's going to happen is some of the different wavelengths will absorb energy, or some of the photons will be absorbed by electrons being excited to higher levels. So that's going to remove particular wavelengths of light from the spectrum of the visible light. The wavelengths that are not removed manage to get all the way through. So here, instead of seeing this, what we would see is a Roy G. Biv with black lines where these colored lines are, and colors where the black is shown on this particular diagram. So that would be an absorption spectrum. In fact, I'm going to try and pause this and pull up an absorption spectrum versus an emission spectrum. So let's see, let's do a pause. Okay, so I went online and I found a hydrogen absorption spectrum and a hydrogen emission spectrum. If you take a look at the bottom spectrum, that's the emission spectrum. So that is a hydrogen lamp with electricity pulsing through it so that the electrons are excited. And as they relax, they emit photons of a specific wavelength of light, which is what we see. Now, the reason we don't see colored lines all over the place there is because only particular relaxations are allowed. So because of the discrete distances between the different orbits, you have discrete wavelengths of light and discrete energies. Now, above, you'll notice we have what looks like mostly the visible spectrum with some black lines running through it. And those black lines correspond exactly to the colored lines in the emission spectrum. So in this case, you have a hydrogen lamp and visible light coming through it. So what manages to make it through the hydrogen lamp? All the different wavelengths of light that are not being absorbed. So what wavelengths of light are being absorbed? And the answer is the ones that are specific for the electron moving from one orbit to another. All right, so that's the model of Bohr's model of the hydrogen atom. I want to make sure that I'm doing the correct share. There we go. And need to make a little adjustment here. All right, let's take a look at this first question based on Bohr's model of the hydrogen atom. What are the wavelength and frequency of the radiation involved in the least energetic emission line in the Lyman series? What are the values of n initial and n final? So to do this, we have to find the Lyman series. And here it is in the book, and this is on page 289, and here's the Lyman series. Now, they're asking us for what is the wavelength and frequency in the least energetic. So we're going to say the least energetic, least energy, we're going to use the following. Energy is equal to hc over lambda. So to get the smallest energy, we want the largest wavelength. Okay, so let's take a look at which one of these has the longest wavelength. And here, there's this one here that says 121.6 nanometers, and the others are all smaller. So the largest wavelength is 121.6 nanometers. Okay, so here for the wavelength and frequency, the wavelength is equal to 121.6 nanometers. And remember, to get the frequency, we use C is equal to lambda nu, which means that nu is equal to C over lambda, which is equal to 2.998 times 10 to the 8th meters per second. All over 121.6 times 10 to the minus 9 meters. And we're going to pick up with this in just a moment. Okay, and when we finish this calculation, we have well, I've got to turn my calculator on, 2.998 second EE8 divided by 121.6 second EE negative 9. And we get that the frequency is 2.465 times 10 to the 15 per meter. So that is the wavelength and frequency. Here's the wavelength and here's the frequency for the least energetic emission line in the Lyman series. And what are the initial and final values? They're n equal 2 and n equal 1, where this is the initial and this is the final. And you can see that in the figure in the book. Okay, let's put that off to the side. And let's take a look at this next one here. I'm going to do a little adjusting here because I see something on the screen that I don't want to see. Oh, there we go. Okay, let's see if we can zoom in on this just a little bit, make it easier to see. Okay, problem with zooming in on this is that it gives me less room to work. Okay, consider only transitions. Whoops. Boom. Okay. Consider only transitions involving the n equal 1 through n equal 4 energy levels for the hydrogen atom. How many emission lines are possible considering only the 4 quantum levels? So what we're going to do here is we're going to look at the emission lines. So for A, the fact that they are emission means that they start at high N or large N, and they end at smaller n. So we're looking for n1 through 4. Now I don't like to draw circles for the energy levels, so I'm just going to do n equal 1, 2, 3, and 4. So let's look at the emissions. I'm going to go ahead and start at 4. You could go from 4 to 3, 4 to 2, or 4 to 1. So each one of those lines represents a different emission. You could start at 3 and go to 2, or 3 and go to 1. That's 2 more. Or you could start at 2 and go to 1. Now, why don't I have any arrows going up? Because that would be absorption. And we're only doing emission. So there are 6 lines possible. And if you wanted to write out what they would be 4 to 1, 4 to 2, and 4 to 3, 3 to 1, 3 to 2, and 2 to 1. Those are your 6 emission lines possible. Photons of the lowest energy are emitted in a transition from the level with n equal blank to n equal blank. Now here, for these emissions, it's important to know that the energy levels here are closer together for large n. So if I wanted to draw this better, I do this, n equal 1, n equal 2, n equal 3, and n equal 4. So photons of the lowest energy. Now the distance between these tells me the energy. So this is going to be the lowest energy right there. So lowest energy is going to be n equal 4 to n equal 3. Okay. And which would be the highest energy? Well, 4 to 1. C, the emission line having the shortest wavelength. Okay, so shortest wavelength means highest energy or greatest energy. So which one's going to have the greatest energy? I'm going to use this one above here and say that, well, that's got to be the greatest. So n equal 4 to 1. And there you go. So that's how you answer that one. Okay. Let's see. We're going to do 2 more questions. If energy is absorbed by a hydrogen atom in its ground state, the atom is excited to a higher energy state. And here we really mean the electron in the atom is excited to a higher energy state. I don't know if it's my glasses, but this doesn't seem to be focused. I guess that's what we're going to have to deal with. Okay, for example, the excitation of an electron from n equal 1 to n equal 3 requires radiation with a wavelength of 102.6 nanometers. Which of the following transitions would require radiation of a longer wavelength than this? So for this, it's helpful to draw, and we're going to go all the way to 5. So let's draw these energy levels that don't show the actual differences, but kind of a representative differences. So I'm going to start off here with n equal 1, and I'm going to put this for n equal 2. Now for the energy level, n equal 3 is going to be closer to n equal 2 than 2 is to 1. So I'm going to make this a little shorter. So that distance is smaller. And then I need to make a smaller distance again for n equal 4. And then an even smaller distance for n equal 5. So we're supposed to see these distances getting smaller as we go farther away from the nucleus. Okay, and remember, the nucleus is over here at the bottom, down there. Okay, if energy is absorbed by a hydrogen atom in its ground state, the atom is excited to a higher energy level. So the ground state means it starts at 0. For example, the excitation from n equal 1 to 3 requires radiation with a wavelength of 102.6 nanometers. So from here to here, we have to get an absorption of 102.6 nanometers. Okay, so which of the following transitions would require a longer wavelength than this? So let's take a look at these. 2 to 4. So there's 2 to 4. 1 to 4. 1 to 5. So this is A, B, C. 3 to 5. D. So we're asked which take a longer wavelength. Okay, so let's take a look at these and let's judge them based on energy. So here, this takes a certain amount of energy. Which ones take more energy than this one? Well, we just judge it by the length of the arrow. I think it's clear to see that when we go for A, it's a shorter arrow. Shorter arrow, less energy. B is a longer arrow, more energy. C is definitely a longer arrow, more energy. And D, you can tell that's definitely a smaller arrow, shorter arrow, less energy. Okay, so we can tell by the length of the arrow how much energy it is, but we're not asked about the energy, we're asked about longer wavelength. Well, it's important to remember that energy is equal to hc over lambda, so longer wavelength means smaller energy. Or we could say the reverse. Smaller energy means longer wavelength. Now, we want to know which are going to be a longer wavelength than the following, than 102.6 nanometers. We take a look at this. We're going to look for those with a smaller energy because they will result in a longer wavelength. So it looks like here we're looking at B and D require less energy. Therefore, longer wavelength. And there's your answer. Okay. Calculate the wavelength and frequency of light emitted when an electron changes from n equal 4 to n equal 3 in the hydrogen atom. What region of the spectrum is this radiation found? We're going to go ahead and do this one. Now remember, the energy of the nth level is negative RHc over n squared. So we're going to use this idea and the n equal 4 and n equal 3 to calculate the wavelength and frequency of light for this. Now, we're going to do this, that the change in energy, we don't need the n here, is going to be the energy final minus the energy initial. So here, the energy final is going to be negative RHC over n final squared minus negative RHC over n initial squared, which is equal to negative RHC over 1 over n final squared minus 1 over n initial squared. So this allows us to calculate the change in energy if we use this formula. So let's calculate the change in energy that occurs for this type of change where you go from the fourth to the third. So the change in energy is going to be negative R, negative 1.0974 times 10 to the 7th meters to the minus 1, 6.626 times 10 to the negative 34 joule seconds, and 2.998 times 10 to the 8th meters per second. So these meters cancel, these seconds cancel, and we'll be left with joules. The final state, we go from 4 to 3, so we're going to have 1 over 3 squared minus 1 over 4 squared. So let me find my calculator. What did I do with it? We use this value again and again and again, so let's calculate that one first. Turn this on, clear it, 1.0974 second EE 7 times 6.626 second EE negative 34, and then times 2.998 second EE 8. So I get 2.17 or 80 for significant figures times 10 to the minus 18 joules times 1 over 3 squared times minus 1 over 4 squared. Now, remember the negative. We want to bring that down. So let's see what we get here. Times parentheses 1 divided by 9 minus 1 divided by 16. And parentheses, and we get 1.05 times 10 to the minus 19 joules, and that's going to be a negative. So this means that it's energy emitted. Okay, so that's the change in energy. Now, how do we use that number to calculate the wavelength and frequency? Well, here we go. Let's look at the frequency first because it's going to be easier. So the frequency. We're going to use E is equal to lambda nu. So the frequency is going to be E divided by H, which is negative 1.05 times 10 to the minus 19 joules over 6.626 times 10 to the minus 34 joule seconds. Okay, so let's see what we get. Divided by 6.626 second EE, negative 34. And I get 1.5 or 1.60 times 10 to the 14th per second. So that's the frequency. Now, what about the wavelength? Well, the wavelength is equal to, because nu wavelength is equal to C, the wavelength is equal to C over nu, which is 2.998 times 10 to the 8th meters per second, all over 1.60 times 10 to the 14th per second. So let's see what we get here. So here I get 1.60 1.87 times 10 to the negative 6 meters. Now, this is the wavelength. This is the frequency. And now all we have to do is calculate. Let's see. The other thing we need to answer here is, what region is this found in? So let me show you how I would do this. I would take my wavelength, 1.87 times 10 to the minus 6 meters, and I'd multiply by 1 nanometer over 1 times 10 to the minus 9 meters. So divided by 1 second EE negative 9. And we get 1875, or I'm going to call this 1870 nanometers. Now remember, the visible spectrum goes from 400 to 700 nanometers, and longer wavelength of that would be infrared. So because this is below 3,000 nanometers or 4,000 nanometers, I'm going to call it infrared. And there you go. All right. Thanks for listening.